All right, well, I guess I'll get started. It's a smaller class than usual, but exam mature-ish time, I assume, still. So today the main topic for today will be about signal conditioning, which is how we read some of the analog sensors. So this will be important for things like the light, ambient light sensor or other sensors you want to use in the robot, as well as some general principles for using them in the future. Before we get into that, I had earlier said that I would have details of the progress report today. So this is basically as was originally posted. There's no real changes. The only other change was the mention of the updated deadline of June 30th, 4 p.m. Either there'll be an online submission all set up, or again the same mailbox you've been using. If you look back to the grading scheme, you'll see that there's only the one progress report, and it's directly worth, I think, 15% of the grade. So it's a fairly high, worth quite a bit. So definitely plan on trying to submit it a little early, just to, get rid of any chance of things going wrong, buses late, or computer crashes, or something else. The other important note is that at the beginning of the course and in the course outline, it references the Dow's plagiarism, intellectual honesty policy. The rules on that will be strictly enforced for this report. So if you plagiarize, if there's two reports that are the same, I'm not going to ask you to explain it. I just will submit your name to the academic discipline committee for it. Because this is such it's worth so much of your grade, there's really no chance to sort of get around that. So for other stuff, sometimes I'll ask you if you're like, hey, this looks suspiciously the same, but for this, there won't be any of that. It'll just be directly reported. So I really encourage you to get started on this early so you don't either miss it and just lose 15%, or be tempted to copy. And this also means that you should, if you reference things, so if you're going to use code, or you're using code, or you want to use a diagram, you just simply have to reference it to make sure there's no risk of that accidental plagiarism. So you're allowed to use in your report. You might say, here's an interesting, some results I want to duplicate, or something like that. That's fine, as long as you make it clear that this is someone else's work you're using and not your own. So the topics to cover on it, there's a 5-page maximum for the actual report content. And there's no minimum, so however little you can get away with is fine. There's 3 additional pages allowed for sort of appendices. So the report itself has to be within 5 pages. I don't have to read the additional 3 pages, but this could be stuff like, if you want code, so you say, here's an example of a routine I'm going to use, or here's some data from a proof of concept test we did, something like that. So something that I don't necessarily need, but if I want to believe you more, it would be useful. So they're more for information, but I won't read anything beyond the absolute maximum of 5 pages, and I encourage you to try to be as brief as possible and cover all the topics. So what are the topics? The topics are basically the following, 4 sections. At the beginning, you should have an executive summary. So this is basically a shorter version of the entire report, so you can see what it includes. A short statement of what your interpretation of the project is, what period and phase this report's covering. You want to talk about sort of problems you've addressed. Again, everything's about up to this point in the course. So what work you've done, what is sort of in progress at this stage, and you also will reference, what will be done before the end of the next reporting period. Obviously, this part will be highly subject to change. So this is part of your planning. You should have some idea what you're going to accomplish in the next period, but you won't, if you say something and you do extra, work, or you end up not needing to do some of the work you planned, that's fine. Don't take this as you must follow this plan exactly. It's more about showing there's some reasonable plan you have done. So that's just the executive summary, is a very, very brief version of this that I could read in half a page or less, or however little you can get all this information across to the reader. The rest of the report is basically more detail on everything in your executive summary. Again, you'll talk about the design stage of the project. So this is just where you are in the progress, and material covered in this report so far. And again, all of this is in the original syllabus too, by the way, if you want a reference of these, and the slides will be posted. The discussion, this will be the bulk of your report, really. So this will be talking about some detail of what you've completed so far. So this could be, you know, we got the robot to drive forward, or we played with this sensor, we, you know, have done this code. You want to talk about problems encountered during this period. So this can be both problems that you solved or problems that are really delaying you right now. Both of those you want to talk about. And you know, the delaying part will involve probably ongoing work as part of that, things we're trying to fix. One thing you have to reference is there's some sort of schedule you need, so you have to figure out what your progress is in terms of the schedule. I'll talk about that separately. The schedule can be something like a Gantt chart. That's a really easy way to show, you know, here's the various tasks, but if you really don't like them or you don't want to use one, you can cover the same information in other ways. So you could have a breakdown. Here's the work breakdown structure. Here's, you know, a list of tasks, subtasks, anything that communicates, you know, here's what we have to do. Here's the time we're estimating for each one. Here's who is going to do each task or subtask. And that will also then, the schedule will include the future work that you're going to be undertaking. So, you know, I'm going to do this, my partner's going to do this, or, you know, whoever's doing this and this, when we're hoping to have different areas done. So that's sort of the future work. And then you can conclude with, you know, very briefly, how's your progress been made to the schedule, summarize some of the progress made in this reporting period, and a little bit, if there's sort of the important part for the conclusions, is that if something's going, you know, really afar, like you haven't got your robot moving at all yet, and you say, oh, it's almost the 1st of July, we should have got our robot moving, here's why, you know, something broke, or we were concentrating on getting the sensors working, and here's what we're going to do to get the project back on track. So yeah, as I mentioned, it has to include a schedule. I'm not really concerned with the exact format of that. As I mentioned, the Gantt chart is one of the easier ways to show all this information in one spot, but if you have an alternative that you'd prefer, feel free to use that. And when you reference things, so if you want to reference, you know, material outside of the course, or code samples, stuff like that, I don't really care about the format of these references. It just should be reasonable to show that you're using other materials, and make it possible for me to find the source material. So if you just say, like, you know, one title vaguely, that's probably not enough of a reference. It should have, you know, the title, the author, or a link to where you got it, something like that. So it's important I can find the source material, and you've made it clear this is some sort of source I'm using. And that includes code samples and stuff like that too, or example circuit diagrams. You know, it's not unreasonable that you're going to be finding examples for the sensors or the robot. That's fine. You don't have to try to make it seem like you've done everything yourself. I fully expect you to be using existing code or using samples or using other people's work, as long as you show that, hey, I found this, you know, example for the pulse width modulation code, and I just used it. That's fine. Other announcements, a while back I said on Tuesday morning the open source stuff would be posted. So that was posted. There was no other announcement. And it's more or less what was discussed in class. So the idea with this is that if you make a project that meets, there's several projects posted. Basically you have to make something that'll meet the requirements here. You have to explicitly allow other students to use this code. This basically means releasing it under what's known as an open source license. If you're not sure how this works, you can email me or ask on the forum. But basically, you just put in a license file that says, hey, this work is by me, so you still have the copyright of whoever did it. But you're allowed to use or redistribute it in source code or binary, the executable. And it just has some disclaimers. So it says, you have to retain this copyright, so you have to always know who wrote it. You have to reproduce that notice saying this work I'm using was written by someone else, and there's always the disclaimer, everything's as is, no warranty, stuff like that. So the first person, if someone makes a project that does one of these things, the projects, for example, it's like design a motor driver or something like that. Only one group can receive credit for the project. So once a project is posted, it's no longer eligible to have another solution posted. And one group can only receive credit for one of the projects, whichever the first one they submit, they'll receive the credit for. They could post solutions to the rest of them and it'll just nullify them. So I don't think people have that much time, though, I doubt. In the projects, you can only use parts from your 3901 parts kits. There's varying deadlines for the projects from the 1st of July onward, basically, is the deadlines. And what else? And I think that's the basics of the rules. They might be updated slightly, but the idea is just to encourage up to one project per group and post it in a timeline that everyone can use it. And all the projects have to meet these requirements, so you have to have full, well-commented C or C++ code, and it has to be possible for someone to use your code without copying and pasting stuff into a separate file. So this means you need modular source code files. So if you're doing a motor driver, you need like motordriver.c and motordriver.h. As part of the project, it has to have all the documentation, which includes how do you external hardware connections and stuff like this. So someone that gets the files, and I'll be looking at them, so I'll take them myself and say, could I use this to use the documentation you provided to use your files? And there also needs to be a simple demo, so you can just make one main.c, or similar that runs your code, and you can say, here's how you'd use it, here's how you'd use all the features. So if you don't do this, it's basically just considered incomplete, and the project doesn't close until there's a complete project. So if you submit a incomplete project, and I look at it and say, oh, that's not, you're missing a few things. If in the meantime someone else submitted something that was complete, you miss out. So because these are bonus ones, there's some sort of, the rules are pretty strict in it. So it doesn't guarantee any sort of priority, and I'm going to look through them very carefully. I sort of warn you somewhere that a lot of these projects are fairly in-depth, and because of the requirements, it's possible you could spend a bunch of time on this and then someone else submits in time. So I sort of warn you that only if you have a fair amount of spare time or already have some of this working, I'd encourage you to submit. Because it's not, it's not as easy bonus marks or anything like that. But it still, I think, is an interesting spin to the competition. So what the heck are the projects? The first, there's 5 of them, I think 5 or 6. The most basic one is the motor driver, so you have to use a specific API for turning on the left and right motors to certain speeds. Okay, you must strictly follow this API, so this must be in your header file. You can provide other functions if you have them, but if you don't provide at least these, then it's not considered complete. So the points and deadlines vary depending on the complexity of the project. So the motor driver, for example, gives you 1 additional point on the competition day, which just corresponds directly to 1% on the final grade. So all of these are percents on final grade. Dead reckoning solution. So this involves both a 3D printed encoder wheel, which has to at least include the STL file or the SolidWorks assembly, which they can use to print here. How to sort of set up the board, so the documentation on here's the resistor values, here's the how to wire the encoder, and some software on the microcontroller. And the software is simply counting how many ticks of the encoder have passed, and someone can directly use that to figure out how far each motor has traveled. So all you would do is you'd reset the tick count to 0 and drive for a little while, and then you could say how far has the left motor spun or how far has the right motor spun. So there's not a lot to this one, and the ticks, the user will have to be careful because you haven't actually dealt with going left or going forward or backwards. So to use this module with the motor driver will require the user to do a little bit more hacking, in that they'll have to figure out, hey, when the motor's spinning forward, I have to increment one of these ticks, and when the motor's spinning backwards, I have to decrement it. So there's a lot of these projects are mostly complete, but it still requires people to think a little bit about using them. I don't want it to be, someone's completely solved everything for you. The third project, this is the most complicated, so this is a tilt compensated compass. So this is a little bit of what you did in the lab, except it adds the ability to, using the accelerometer to measure the pitch and roll of your robot platform. And then based on that, there's some mapping of the compass from the navigational frame, or from the sensor frame to the earth frame or northeast down frame, and then doing the compassing information. So this is referenced in some of the solutions to this are in a paper I'll post later today. But there's a fair amount of math and a fair amount of experimentation to verify that your solution works. Basically, the answer to if it works is, can I take the robot, not only can you, rotate it around and it works, but I can tilt it on 45 degrees and rotate it, and the compass information stays accurate. So that's the most complicated. Gyroscope integration. So in the lab, you saw that little well loop that, just added up, did the gyroscope integration. The well loop wasn't always accurate on time, and you couldn't do anything else in the well loop or it would disrupt the timing, causing inaccuracies. Instead, if you set up an interrupt using one of the timers, you can do this integration on a very constant time. So you can, every 200 milliseconds or 100 milliseconds, you can read the gyro and integrate it. So this project is just to basically perform that and give a nice API such that someone just calls the setup, calls the calibrate that nulls the biases out, and then they can reset the angle whenever they want and read how much change has been from that angle. So very simple. How many is there? 5, 6? Oh, 5. So number 5, this is another simple project, so it's only worth 1 point. You can see the tilt compensated compass is worth 4 points, or 4% extra. So this one is just for the ultrasonic rangefinder, doing the timing of the echo response, so it's pretty simple. Again, there's a specific API you have to provide. Finally, we'll cover today how to do some of the stuff you need in this project, but to differentiate between 3 frequency sources, as well as determining the approximate location of a light, so is it to the left or the right of the robot. And this is, again, using all parts in your parts kit, plus I believe you can use resistors and capacitors as needed as part of the competition. So if you need additional resistor values, that's fine, and I'll update these to explicitly say that. But basically, you must be able to, someone has to say, like, hey, what's the magnitude of a 500 hertz or a 1 kilohertz or a 2 kilohertz light, at whatever location in front of me or something, and what direction is that light. So these are sort of a generic API. It's likely you may want to provide additional calls. So when you go through the design, you might say, actually, it's easier to ask what's the magnitude left, right, and center, or left and right only, for each of these frequencies. So that might be the better API that you also provide, and then also have the ones written in the document. So this is sort of the basic projects that are posted. Any questions on that stuff? As I say, it's purely sort of an extra bonus thing. So they are a little complicated and they're not very well defined. But when you start going through them, you may sort of learn more about it and have some questions then. All right. So with that, I'm going to start into the actual material. Today I'll be talking about a few things. Circuit loading. So this is related to when you interface sensors, buffering sensors, input protection for to stop blowing up your AVR, and filtering. So sort of a very brief introduction to designing filters and using them. There'll be a bit more of this either Monday might switch to the metal detector, sorry, which will be the lab on Monday. And then, so this might end up getting pushed to Thursday, but we'll cover this quite a bit because it'll be a very useful, useful sort of topic for your robot, the idea of filtering. So the first thing I'm talking about is circuit loading. And what this is oops, come on. What this is really the question of if you have, you know, a simple voltage source or something like that. Oh. 1 second. If you have a voltage source and you go to measure, this thing's come on, crashing on me here. All right. Restart this now. So if you have a voltage source, in the meantime, we'll keep talking, and you measure the voltage. Across it, you could get the wrong answer if you sort of fall victim to what's known as circuit loading. So if we had a battery here, you know, ideally you just have a voltmeter and you connect it to that, and you know it says 3 volts. That's sort of the ideal solution. So you measure the voltage across the battery and it says, hey, that's 3 volts. In real life, it might not be that simple. There's a few things that you have. Your battery isn't perfect, so has some series resistance, RS. Your meter is also not perfect. So we think of a meter as just telling us, you know, what is the voltage. But in reality, the meter has a small load resistance here. Now, in real, you know, if you were just measuring a battery, the values are so large for the load resistance and so small for the series resistance, it wouldn't matter. So this is typically like 10 ohms, let's say, and depending on your meter, it might be as low as a mega ohm. But if we change these numbers a bit, so let's say we had a, you know, different circuit, and this is actually 10 kilo ohms, and this is 10 kilo ohms here. What you would measure is, rather than measuring 3 volts, you would measure half of that, because you've pulled down the voltage due to this load resistor here. So circuit loading is the effect of the load of, you know, some other part of the circuit affecting your earlier circuit. And this is why, as a side note, if you look at oscilloscope probes, some of them have this 1 times 10 times switch. Some of them do not and are always just in 10 times mode. What this means, and this is sort of important to be aware of, is that the scope probe itself is designed such that if it's a 10 times probe, whether you switch it into 10 times mode or it's fixed in 10 times mode, the signal at the oscilloscope input is actually 1/10 of the magnitude of the true signal value. So if you measure 10 volts, it's 1 volt on the scope. Because this is so common, scopes have a mode that they basically just multiply all the voltages by 10 when they display them. Sometimes you have to tell the oscilloscope that that's what you've done. And the reason we do this, so you might say, like, well, that seems crazy. Why would you do that when we could just keep it in 1 times mode and never have to deal with this? And the reason is related to circuit loading. That's one of the main reasons. So if I look at a oscilloscope probe, this is just a few different probes. So you can sort of, let's look at this guy here, ignore all this. What it's saying is that the scope in 1 times mode presents a certain capacitance. So if I'm measuring a circuit, the scope probe looks like a capacitor. In 1 times mode, it's 85 picofarads. And in 10 times mode, it is like 18.5, so it's much less. So 18.5. And this will really reduce the load on the circuit. So if you're trying to measure a high frequency signal, some of the signal will be attenuated because the capacitor will have conductance at higher frequencies. So we have a lower value capacitor it loads the circuit less. The other thing it does is, you'll notice as well, and this is for almost all probes, the 1 times what's known as the bandwidth, which effectively says how high a frequency can I measure, in 1 times mode is always much lower, so like 4 megahertz, than in 10 times mode, which is 60 megahertz. Or for a different probe, it's 10 megahertz in 1 times mode and 200 megahertz in 10 times mode. So if you're measuring higher frequency signals or digital signals which have high frequency components, you really need to use the 10 times mode. So it does have both, but the 10 times mode is almost always more useful. And that's why some probes just don't have the switch at all. Some do have the switch. But that's sort of an introduction to where you see circuit loading and the potential effects of it in the test equipment you're using in the lab even. The other part that you'll really see it is the inputs to your analog to digital converter. So on your AVR microcontroller, it can read an analog value. And it has, if you look in the data sheet, it has this this analog input resistance. So, which is effectively, for what you care about, you would think like, oh wow, 100 mega ohms, so there's no circuit loading effect at all. The problem is, if you read into the data sheet, it actually tells you that, hey, the ADC is designed for signals, and what they say is an output impedance of approximately 10 kilo ohms or less. So when we say output impedance, what we mean is if you had your signal, if there's some effective series resistance, they're saying this resistor should be 10K or less. And then you had your AVR here. And why they say this is that the AVR itself internally has a what's effectively a large series resistor that charges a capacitor. And this resistor can be up to equivalent to like 100K or something like that. And it'll slowly charge this capacitor, and it's at this point that the ADC is measuring the voltage. If your input is a very high value, so if this is 100K, and you have whatever, a signal here that changes, maybe your light sensor, it's going to take a long time to charge up that capacitor. So if you just had a constant 3 volts, and you can wait a few milliseconds or more maybe, yes, it will eventually measure 3 volts. But if you have a signal that goes, 3 volts, 0, 3 volts, 0, 3 volts, 0, you're not going to see these sharp transitions. And so that's what it says when it means you should have a lower input impedance here, such that it's able to fairly quickly charge up that sample and hold capacitor. So that's sort of another related effect to circuit loading that you would care about in your system. The other thing where you can run into this is in filtering circuits, and filters we'll talk about today. They will often present a fairly significant load. So if you have our sensor over here again, whatever the sensor is, the impedance looking into the filter can be quite low, and this will load down your signal. So you originally had a 1 or 2 volt signal you can easily read. Then all of a sudden at the output here, maybe you have 100 millivolts. And this is because you have a series resistance effectively in your sensor, and the filter is loading down the signal such that it ends up being very small. So to fix this, we can use buffers. An ideal buffer, which we represent with this triangle, would just be that whatever signal goes in, the exact same signal of the exact same amplitude comes out. So if we have a 1 volt signal going in, we have a 1 volt signal going out. And the buffer you can really see is like an amplifier with a gain of 1. So that's kind of what our buffer is. So ideally, it would take the input and replicate it at the output. The difference is that the buffer itself has a very, very low output impedance. It would ideally have infinite input impedance, saying it does not load the circuit at all. At the output, it will drive a very, very strong signal. So you could use this to drive whatever, your ADC or even filters and not worry about the load. That's the ideal buffer. And we can look at how can you build a buffer with parts in your kit in particular. So there's sort of two main methods. The first is a simple transistor buffer. And I'll show you briefly how this works. So this is a transistor configured in what's known as an emitter-follower configuration. So this is a very simple, effectively amplifier with a gain of 1. And we'll see there's a tiny bit of distortion and it's sensitive to what the input signal levels are, but the advantage is it just uses one transistor. So it can be very simple, especially if you just have an on-off signal you want to buffer or something like that, or you're not too worried about a very linear response. So in this configuration, the output voltage here will be approximately the input voltage minus the 0.6 volt drop due to the silicon junction. And there's no real voltage gain, and that's because we have current gain. And you can see this because if we change, so if the input voltage changes by delta V, so say it changes from, I don't know, 2.0 to 2.6 volts. The output is also going to change by that same amount, but again there was this initial a little bit of offset, so I'm saying around 0.6. So the output could go from 1.4 to 2.0 volts. So we've maintained that 0.6 volt delta. And for a lot of sensors, the delta is all you really care about, so that's fine anyway. But what's interesting is that how does the transistor current change? So the current at the output is the current going through this resistor here, and that current change is obviously just going to be the change in voltage divided by whatever that resistance we choose here is. Now the important thing to realize is that in a transistor there's a relationship between the base current here and the current through the transistor, or the collector current, IC, IB. And the approximate relationship between this is the collector current is this current gain figure beta divided or multiplied by the base current. And this figure is normally quite large. So if we change the base current by 1 milliamp, the collector current changes by 100 milliamps or something. What this means to us is that for this given current change here, the base current changes by 1 over beta. So the base current, if the collector current changes by 100 milliamps, beta is 100. The collector current changes by 100 milliamps, beta is 100. The base current only changes by 1 milliamp. What this means is that the apparent load, so looking in this way, if you say what is the resistance of this system, what's the load equivalent to, we've effectively multiplied this resistor here by the current gain of the transistor. So this resistor here, you can look at as our output impedance to some degree. So this is, how strong can we drive a signal? So we can make R some smaller value, like 300 ohms or something. Even though at the input we have a sensor that has a very large the source resistance. Has very large source resistance, and then we're able to drive a stronger signal. So you would see this when you're looking at your phototransistors, for example. The phototransistor itself, you often had to have a, like 1K or larger resistor, and it depends how fast you want the whole thing to respond. Plus 5 volts. So we have a phototransistor, and it has a fairly large source resistance, so it has trouble. It would be loaded down very easily. So we could connect that to a simple emitter follower and potentially have a more powerful output. So that's just a very, very simple example of a circuit that you can do with a single transistor buffer. So as an example, in your kit, you have this 2N222A transistor, and it gives you this DC current gain figure of, so it varies with, it's important to realize these current gains are not constant at all. You don't want to design a transistor circuit, you don't want to say my circuit only works if beta is 75. It varies with everything, with the transistor you have, as well as temperature, current through it. So in this example, you can see, if there's a milliamp of current flowing, it's about 50. If there's 10 milliamps, it's about 75. And it gives it a different, that same 10 milliamps, but at a colder temperature, it goes way down to 35. So it varies a lot, but you can see it's always around this, 50-ish, 30 to 50 to 100, depending how much current's flowing. But what this means is, in reality, this, we're going to multiply that 300 ohms times something like 50. So now, rather than being a 300 ohm load, it'll see, even if, what was the ranges here? So if we were at the upper range, like 100, you'd be talking about a 30K load. Maybe it goes down to 15K if it's around 50. But it's a much bigger load that this system's seen, so it's not going to load your sensor as much. And that's just with one transistor and a resistor. If you want to simulate it, so I'm going to use something called LT Spice, and it's a totally free circuit simulator. There's some online solutions too, so this partsim.com has them. So these, you can actually build a little circuit, simulate it, and see how it works. And this is important because when we're looking at the transistor, I've sort of just vaguely drawn some stuff on the diagram here, but there's some considerations. It will only work within a certain voltage range at the input, for example. And if you have a circuit simulator, that's a really easy way to check you've set up things properly, you have a sufficient current flowing through the collector of the transistor and stuff like that. So it's important to do these simulations. So as an example, I just built, a simple sensor. So what my sensor is a sine wave. So that's the voltage source with a 220K resistor. So this is effectively what the series resistance is of my sensor. So the sensor can't provide very much, or can't handle very much load at all. At the output of the sensor, you can see the span is from like 2.3 volts to 2 volts, somewhere around that, or maybe a little something like that. So you can see there's quite a large signal, but then when I look at where I'm measuring it, which is once I've added this 10K load, so I'm saying that, it goes through a filter or something that has about a 10K load. My signal swing now, you can see, goes from like 116 millivolts to 100-ish. So we have like a 16 millivolt swing. So that's going to be a lot harder to detect, and there'll be a lot more issues with noise. And again, this is assuming that resistor is sort of replacing a filter. If I simply put that really easy transistor in here, so that the 222 that's in your kit, and again, I have that 10K load here, but I also have, in this case, I've added an explicit emitter resistor here, the emitter follower configuration, and you can see even with this really simple circuit, we've now got a swing, from 1.71 volts to 1.38. So I haven't tuned a lot of stuff, and there's still some diminishing of the amplitude, but we have a much bigger swing here. So now we have, what's this, 1.7 to 1.4. So we have a pretty similar change in voltage to the input. So we have about that 0.3 volt change. So there's a bit of a shift at what the center point is, which you expect, but we've maintained that delta V. So that's what I had said earlier, is that if we go back, there's going to be this change, this 0.6 volt drop due to the junction voltage, but the change in voltage should remain about the same. And we can see that, oops, not this one, in this one between the input and output. And again, that's just one transistor and as an amplifier. So that's a very simple circuit. And any questions on the transistor stuff before I move on? Okay. The other option you have is operational amplifiers or op amps. So you have 2 of them in your kit. Each one has 4 op amps in it. So you have a total of 8 op amps. One op amp being this, the little triangle with plus minus. And we'll talk a little bit more about these later. But very briefly, there's 3 terminals to an op amp. And the objective of the operational amplifier is it controls V out at the output. So this is the output of the operational amplifier. And it is simply going to attempt, by controlling V out, to make the difference voltage between these 2 terminals be 0. Diff V equals 0. So in this configuration here is the sort of easiest use of an operational amplifier. Whatever voltage you set at the input, it's going to attempt to control the output voltage to make the negative terminal the same as the positive. The operational amplifier doesn't know what the exact relationship is. It doesn't actually care. It's simply going to try changing the output voltage until it matches the input. So in this configuration here, what you end up with is a very simple buffer where whatever voltage you put in at the input equals the voltage at the output. So we just have this, V out equals V in. So it looks almost like an ideal buffer circuit. There is a few sort of non-ideal considerations. So the first one is that the maximum peak output voltage has a limit based on VCC. So you can see here they're using plus minus 5 volts, for example. If we power it from plus and minus 5 volts, in your robot you may only have plus, but you may have a slightly higher voltage, the output, the maximum output voltage is only like 3 volts, maybe a little less. So we can't even get the full range. And so this is what they call this headroom, which is the difference between one of the supplies and what the maximum output voltage you can get. And this is on both the positive and negative side. So if what is that? Is that about 3? So I don't know the exact, I think that's around 3. So in this case, there's about 2 volts of headroom. So you could say, if this, and you can measure what it exactly is, 2 volts of headroom. What this means is that if you have an op amp, if you try to power it from 0 volts and just 5 volts, so what you'll see is you'll need to use higher voltages, the output can only go from 0 volts, or from 2 volts above the negative supply, which in your case is 0, to 2 volts below the positive supply. So the output of your op amp can only really go between about 2 to 3 volts. It simply has these limits in what voltages it can represent. So how do you solve that? There's a few ways. One is that if you can get a negative voltage, so if you can tap off your battery pack, you might be able to get like minus 2 volts here, or minus 1.5, for example, if you just take one of the batteries at this side. And so now the minimum voltage you could go to is going to be closer to 0. It's not quite going to be 0, but maybe you get 0.5 volts. And ideally you'd want a higher upper limit. You may be limited by your batteries, but if you could put this up to 6 volts, then you'd have the ability to swing between 0.5 volts and 4 volts. So you'll have to get a little bit creative with how to power the op amps to use them without running into this headroom issue. The other thing is to do what's known as a virtual ground. And in this case, I'm actually using one op amp to generate a voltage level that's halfway between my two rails. And so this means that I had said the headroom, it's a symmetric swing. So what I might want to do is design circuits such that their 0 volt is actually at halfway between my VCC. So at 2.5 volts if it's a 5 volt system. And then I get the same swing plus and minus, but now it's relative to this VCC over 2. So this is what we call a virtual ground. And this is fairly common in op amp circuits. To use this, you may need to do what's known as AC coupling, the inputs and outputs. So the output of your sensor, for example, might be, maybe it swings negative. Maybe it's if you had something like a transducer, that's not uncommon. So we have 0 volts, and it goes from plus 1 volt to minus 1 volt. And we want to shift that up to the 2.5 volts. So we want to shift it to the virtual ground. So we want to go from 1.5 to 3.5 volts, such that the 0 voltage is that 2.5 as before. And you can do this through AC coupling, and you may have to do this at different stages of your op amp. AC coupling is just simply we put a small capacitor, and the value depends on the frequencies, but I think you have 0.33 microfarads would probably work. Between the two signals. So this is from our sensor here. And the other side of the signal, on the other side of the capacitor, we can specify the midpoint just by using a bias voltage. And you can either, if you had that VCC over 2, and then this would go on to the op amp. You can simply do this with a resistor. So now the drive strength becomes limited. If this is a 1K resistor, this is your effective sort of series resistance. But it's helping to pull that signal into your virtual ground. The other option you could do that's even easier is you could, for example, just use 2 resistors, and you wouldn't want them to be too small. 10K. And a 10K, and you have it between VCC and ground. So what's going to happen is these 2 resistors are setting up a voltage divider, and it's taking your signal. The capacitor is doing what's known as AC coupling, which is to say it's removing the DC component. It's removing that 0 volts or 10 volts, whatever the normal value of it is, and it lets you choose a new midpoint here. So this AC coupling you can even use between op amp stages, for example, if you need to shift things around. It would be useful too between the sensor and your op amp, or your op amp output and the AVR input. The other thing you'll have to be careful of is the possible voltage swing to the AVR output. So you might have something like this. Your AVR is powered by 5 volts, and your op amp is powered by 7 volts, or maybe you have a higher voltage, let's say 9 volts, just for this example. If you power it by 9 volts, the op amp can actually swing at the output. It could go up to 7 volts. You might say, well, I don't have a signal that high going in, but it could be there's an error, your signal's floating, something like that. So what's going to happen is that if you put 7 volts into your AVR, it's not going to be happy. The input pins have a maximum spec, we'll see later, that's something like the VCC, the 5 volts plus 0.7 volts. And if you exceed that, you're liable to just destroy the device entirely. So the easiest way to fix this is to use what's known as diode clamping. And this is a really simple diode clamp. All this one does, and we'll see more of them in the protection section, is limit. So if this is at 7 volts here, so let's say we have this 9 volt VCC, so we get 7 volts. What's going to happen is the diode will actually start to conduct, because the one side of the diode is at 5 volts. So above if you remember, diodes start conducting when there's more than, it varies on the diode, but around 0.5 to 0.9 volt difference. Normally we say about 0.7 volt difference here in the correct orientation, which there is. So this pin here will now be limited to only going to 5.7 volts because it'll start conducting and feed power into the supply. To use this, the only really critical thing is that I have a resistor here. If you don't have this resistor, what this resistor does is limits the amount of current that can flow through that diode. So the current flowing through this, there's a bit of a voltage difference here, is just equal, to the 7 minus 5.7 over, if that's a 1K resistor, over the 1000 ohm. So I should change that to I diode, or I resistor. So there's going to be a limited amount of current that flows. The problem is if you do not have that resistor, if this was just a direct connection, what would happen is you would put 7 volts here, and depending which power supply is more powerful, you could still end up with 7 volts here, and the 5 volt supply will actually get pulled up because this diode will have started to conduct. At the other side of this, there'll be that 7 minus, what's that, 6.3-ish volts. If this 7 volt supply has more power, and it'll actually pull up your entire AVR supply to 6.3 volts, so which is beyond what the limits of where you should be using it. And that's because this could be a very strong, potentially a very strong signal source. It depends on your exact system, but to avoid that, you really need to ensure you have a resistor in there. And then now you no longer have this issue. You don't have to worry about your AVR blowing up. Another type of buffer that just sort of briefly mentioned to know about is isolated buffers, and you actually have these, you have opto-isolators, they're called, in your kit. So normally they're used just to transmit a digital signal on or off, and there's no concern about, they're nice because if you have, you can set it up such that you can have 100 volts here and you have a suitable resistor to limit the current, and on this side of the opto-isolator, all you get is a very small, weak signal because you're just getting the output of the phototransistor. There's a physical barrier between the two, so you can actually get thousands of volts of difference and not have to worry. You can also use this even to put across, quasi-linear signals or an output that's related to the analog input. It requires considerable drive strength because you're talking a few milliamps in to cause the LED to work, but it still is a type of buffer. And where you really often see these is in switch mode power supplies. In switch mode power supplies, we have two sides. So we have one side that's high voltage, and if you're talking about in European voltages, where they have 240 volt systems, after they rectify it, you can get up to 300 or so volts on one side. And on the other side here, you have like your iPhone charger or something. So it's something that you're very close. You have the cable in your hand and all this stuff. So you want to make sure there's no way that if there's some sort of error in the supply or a surge, voltage surge, you don't end up with 300 volts in your hand as you're trying to plug in your phone charger. So what you'll see in power supplies is they use these opto-isolators as a form of this buffer. And they use it to provide feedback, in the circuit. So it's telling one half of the circuit what the output voltage is to do the regulation properly. But so you can see if you look at the circuit board, you'll see, and this is the underside of it, but there's actually an opto-isolator right here. And you also see sort of slots in the circuit board. These are to prevent voltages from arcing over. So you see some slots here, and there's one under the opto-isolator as well. So opto-isolators can be seen and used as a form of a buffer. In this case, we're not using it necessarily for the circuit loading effect, but for buffering the one side of the circuit entirely from another with no concern about voltages crossing it. But the objective is the same. We have an input on one side, we want to have the output on the other side. Right. So I want to take the input protection that I mentioned for the AVR, so this stuff here, and take it even further and sort of generalize it a bit. So I was previously just looking at, hey, we could get a positive voltage that goes up to plus 7 volts. That's not good. We can look even more generally about what about excessive voltages of any types on the inputs or on the power supply rail. And how much protection we need depends on sort of how reliable we want the device to be, what the cost point is, and stuff like that. Because there's a whole bunch of possible expected transients. ESD is the most common, electrostatic discharge. So you're walking across the carpet, you touch something, you get the spark. It could be reverse polarity, so can you connect the power supply backwards to the device? It could be the incorrect voltage, so if you've ever had a device with a generic looking power brick and you have something else that uses the same type of plug you can plug into it, it's bad because the voltages could be totally different. You could have two different laptop power supplies that happen to plug into the same computer, but one's 10 volts, one's 22 volts. So will it protect, if you plug the 22 volt one into the 10 volt laptop, what happens? Probably not good. Maybe they have protection against it, but laptops are designed pretty cheaply normally, so they might not. You also get voltage surges, so that's, lightning strikes and stuff like that. If you're running off AC power, there's going to be surges in the power grid. Or even in DC systems, as parts of your circuit turn on or off, you might get such surges. Finally, we might have issues like, is the input to the system applied even when the power to it is off? So if you look at a multimeter in the lab, you wouldn't expect that, if the meter's off and you probe a circuit by accident without turning it on, you wouldn't expect your meter to blow up. It should be designed such that even if the meter is off, you can still probe something, because maybe you left it connected, to your circuit, and you're just turning everything off. The circuit's still on, the meter's off. So it's going to be designed to work fine, hopefully, when the power's off, but the meter's still on. If it's a poorly designed meter, that might not be the case. Or if you get a type of meter where, if you can switch the mode dial, some of them will blow up if you have it in the wrong mode and you're measuring a high voltage. So I can show you that. I'll show you that afterwards because I don't have the link right there. Going back to the ESD, so for CMOS devices, it's physically damaging inside the device. So this is a microscopic view of the CMOS device. You can see, so these are sort of some of the metal layers here on the chip itself, and we can see there's this big sort of burn mark, holy type thing here. And that's from the metal layer is actually melted, and the risk is that it can melt together and short out other parts of the chip. And this is all from an ESD discharge. A fairly extreme example, not of ESD, but of just changes, variations of voltage, is the automotive environment. So this is from an app note showing what are sort of the most extreme things you might see in a automotive environment. And they're saying, well, there's normally the voltage of around 14 volts. With it running, can drop way down when you start the car. You could have stuff like what they call this load dump. So this is where if the battery was disconnected with the car running, the alternator is continuing to spin. There may not be the load to charge the battery, so the voltage could go way up to, like, they're saying 120 volts. So normally 14, easily up to 120. We can have big noise. So the noise will be, won't have as much energy as we'll see, but will still be very high voltages. When the alternator is kicking off, we might have very large negative spikes. And they say it could even be something like someone puts the battery in backwards. They connect the positive and negative backwards when they're installing it. Should your car survive, like if someone does that by accident, does it just destroy all of the electronics in the car? Or if someone uses a 24-volt battery or system, like if a truck's jump starting you and all they have is the 24-volt battery, should your system survive such extreme overvoltage? And so it's a question of how much money do you want to spend to protect against all this. The different types of those transients, it also gives you an idea what we're calling the energy behind it. So this is the really critical one. How much energy do we have? Because something like the electrostatic discharge, which is very high voltage, it could be kilovolts, it has very, very small amounts of energy. So they're saying 10 millijoules, which is easier to dissipate because all of this, at the end of the day, will have to dissipate somehow, probably as heat. But something like this load dump, so that was disconnecting the battery when it's running, could have greater than 10 joules of power, so that's quite a bit of, or energy, sorry, quite a bit of energy in the system. And of course, if you do something like the jump with the 12-volt battery or the reverse polarity, it's almost infinite energy because you have a whole battery connected to your system. So unless the cables melt or something, it's going to keep dumping battery in. So those are the two real specs you need to consider is the voltage amplitude and the energy capability. You may also worry about the speed of the transient or the length. So is it a nanosecond? Is it a millisecond? Is it a second long? But the energy and the voltage will define a lot of what sort of protection systems we can use. For the most basic protection, we can use what are known as the built-in electrostatic discharge diodes. So as I mentioned, the AVR microcontrollers, they have somewhere it has voltage on any pin with respect to ground. So it says you can go from -5 volts to 0.5 volts, or minus 0.5 volts, sorry, to 0.5 volts above VCC. If you exceed that, it can destroy the device instantly. Basically, it's not guaranteed. It may destroy it immediately, it may not, who knows. So inside the microcontroller, there actually is what's these diodes. These diodes are on each input pin. They're sort of an artifact of the design. They're not explicitly there. But what this means is that if you put in 6 volts here at the input pin, what's actually going to happen is this diode, and your VCC is 5 volts, this diode will conduct, and it'll be conducting some current through the diode. Now, if you have very limited current on the input, so if I have 6 volts, a 47K resistor here, what's actually going to happen is it's going to clamp your input to some reasonable level. So it'll say keep it below that 5.5 volt minimum level. Even if this is 10 volts, something like that. The risk is that very, very limited current can flow through these diodes. So in this example, you could say, well, how much current's flowing? It's depending on that current limiting resistor. So it would be the 10 volts minus 5.5 volts over 47,000. And generally it's around 1 milliamp is the maximum you'd want to allow. Atmel itself doesn't specify explicitly what these are, so you can't use them, you wouldn't want to use them in a product that requires the reliability because there's no guarantee that they will stop any current like this. So what you would want to do instead is add external diodes, and we're just replicating the same thing as we did before. The advantage of these is we have a specification on them, so we can look up and say how many milliamps can we pass through them, or what's the voltage rise going to be. They're fully specified, so now we can be more confident that our system will be protected. When using them, of course, you have to, as before, you really need a series resistor here. And this is, once again, to limit the current. If you don't have the series resistor, the problem is that if you put 10 volts in, 10 volts is just going to flow through this diode and possibly pull your VCC up to 10 volts. So you need something to limit that current flow. It will also burn out the diode very quickly, assuming your input has some strength behind it. So instead, you put a small resistor, and the value depends on what your input, how fast it's switching and stuff like that. For everything you're doing, probably 1K is fine. You could go a little lower if needed. And this will protect both against positive and negative excursions. You may want, as I showed before, if you know that there's no chance of getting a negative excursion and you only have a limited number of diodes, you may want to simply just do the positive side like that. You can also add a capacitor, so you can do stuff like slowing down the speed of the transient. The problem with the previous one is these diodes have a certain turn-on time. It's very fast, like 4 nanoseconds, but it's still there. So if you had an extremely fast, very high power spike, especially as you get in ESD type things, you may end up with 100 volts getting to this pin. So if this is a 10 kilovolt ESD spike, this diode might not actually switch on fast enough. So what you can do is you can add a capacitor, and the capacitor and resistor will slow down your input spike. And this gives the diodes more time to switch on and then eliminate or dissipate the surge. The other thing you might want to do, so the microcontroller boards themselves have reverse polarity protection on them. So if you put the reverse polarity, it doesn't damage it. And they do it this way. So we have the input voltage, and there's what's known as a series diode. So if we put 10 volts in, positive here, negative here, what's going to happen? That's fine. The diode is forward biased, so it's going to drop a little bit of voltage. We always say around 0.7, varies a bit, but something like that. And your device is going to see 9.3 volts. So not a big deal. Everything works. If you put the wrong voltage in, so if you put negative here and positive here, this diode will be reverse biased, won't turn on, and your system's fine. So it doesn't, no power flows through it, and it doesn't blow up anything. What you might want to do is, you have your breadboard, there's the AVR. The problem is that anything else you do on the breadboard won't have the same reverse polarity protection. So this has the input voltage V in. It also has a 5-volt output, so that would be fine. But if you want to use op amps and you're using the V in directly, if you reverse that voltage, it'll put reverse power on the op amp. So to solve that, you can do reverse polarity protection like this, and you have some of these 400 series diodes in your kit. The other option is to use what's known as something like a crowbar-ish circuit. So this type of reverse polarity protection shorts out. If you have 10 volts going in normally, this diode is reverse biased and not in the circuit. And your system sees 10 volts. If you put the reverse voltage in, what's going to happen is this diode will now start conducting, and it'll actually attempt to short out your power supply. So this method protects it by shorting out the supply when you put the reverse polarity. It's more dangerous. You need to ensure this diode can source enough current for however powerful your power supply is. The main advantage of it is that when you have 10 volts in here, your final device sees that 10 volts. In the previous system, we lost about 0.7 volts to the diode. So it's sort of your choice. If you don't need every little bit of headroom, there'd be no point to doing this system. If you need every little bit of headroom, this might be this might be a better solution. The other advantage is that in this system here, your diode is always conducting and possibly dissipating power if you had a very high power system. Here, the diode only conducts when you get the reverse polarity. So it assumes you have something like a fuse or something to limit the current through the diode to disconnect the power supply though. Another type of input protection, TVS diode. So these diodes are very fast and they actually begin conducting above some voltage. So what we see here is that this is a voltage current curve. So it basically, current is this way and increasing voltage is this way. At some point, it starts to conduct. So it could be, at like, and they're specified at very small voltages, like 5.5 volts, say. It starts to conduct. So how we can use this type of device is that if we have our input here, it's actually providing us two features. So we have our AVR, let's say, and say we have this 5.5 volt TVS. What's going to happen is that if we put reverse polarity as a regular diode, it's going to start conducting. It's save our circuit. But it's also going to detect if we put in too high a voltage. So if we put in 6.0 volts here, it's also going to start conducting. So it's going to limit what the maximum voltage is to the AVR. So the TVS diodes help us limit what the voltage is, which can be really useful for both input protection and the power supply protection. So with these ones too, the nice thing is for input protection, we don't have this concern that is it going to pull up the power supply or anything like that. So if we need, we can't have those series resistors there and might have a lot of energy, they're a good way to dissipate that. All right, so the final thing to talk about today is filtering. So very briefly, filters look at the signals in the frequency representation is what we care about. So all signals have some associated frequency representation. You should have done this in some of the other classes. But the most basic is something like a sine wave. Hypothetically, a pure sine wave just has the single frequency representation. It just represents, if this is a 10 megahertz sine wave, we just have a 10 megahertz frequency component. More complex signals will have different spectrum. So we could have a triangle wave like this. You can see it has a frequency spectrum where the harmonics are going outwards, so there's more than just the single frequency component associated with it. And what we want to do is we want to adjust that frequency spectrum. So we want to say, actually, we only want, frequencies below or above some certain point. And it's this point that we're going to deal with filtering. So we're going to say that we want, we want to deal with only 1 megahertz and below, or 1 megahertz and above. And this is because it's very often that the frequency of interest lies in some small band, some known range of frequencies, and there's a whole bunch of other signals out there, and we want to ignore those signals. It may also be that there's some other signals that are much more powerful. So if we just tried to measure, if we said like, we know our signal is in the 10 kilohertz range, we're just going to measure that directly, it wouldn't be possible because there's at the same point a very strong 1 kilohertz signal. As an example of that, there's these ultrasonic rangefinders you have in your kit. So they use this filtering technique to avoid noise in the environment. So it transmits at around 40 kilohertz, and then it'll listen back at 40 kilohertz. So the only way it knows that it's received an echo is it's just looking around the frequency band it transmitted at. There's going to be other noise, people talking, stuff running in the background, and it's able to ignore that simply because it knows to look only in that narrow frequency band. And it does this with just RC filters. So sections of this input here are doing the filtering as well as the detection of the final signal. So we'll very briefly show you how to design these filters such that you can use them in your robot for performing frequency selective work. The other example is detecting light in a few different ways. So if we had a as in the course you have a light that's operating at a known frequency. So if you say I have a 500 hertz light, and my robot over here has a detector, and I want to detect this light. Well, there's a few other sources of light around. In the gym, there's going to be overhead lights. Let's just put them here. There'll be overhead lights, and there's also windows up somewhere, and the sun is going to be shining through possibly. And this could be a very bright sunny day, and the sun is also going to be entering your robot's field of view. So it's potential that you have these different sources of light all entering into your sensor. And you want to be able to differentiate between that light source that you want to find and all this other stuff. So we can use filters to do that. And there's sort of, in this case, there's a few possible solutions in terms of what type of filter to use. And I'll introduce the filter types first. So generally, we have what's known as a low-pass filter, which is to say, so you can consider this axis, the gains, the output voltage. Below some frequency, the filter is more or less trying to pass everything. Above some frequency, it rejects, so it attenuates your signal strongly. The flip side is the high pass, which is to say low frequencies we want to ignore, high frequencies we keep. Band pass, which is to say we keep frequencies within some narrow band, or it doesn't have to be narrow, but some band. And band stop is we reject within some frequency. Oops. So going back to this, sort of some of the different solutions are you could make a high pass filter. And you could say, I'm just going to accept everything above, say, 200 hertz. And why this would work is that the fluorescent lights, and you might want to go a little higher, say 400. So the lights in the gym, if they're powered by our AC, will probably be at 60 hertz. And sunlight is effectively DC or 0 hertz. So if you put a high pass filter, what you're going to do is you're going to looking in the frequency domain. There'll be a bright sunlight amplitude at DC at 0 hertz. There's going to be another spike at 60 hertz, and this is the overhead lights. And way up here, and maybe it's not that big, at 500 hertz, we have our signal source of interest. And in this, in the robot competition, there's a few different frequencies of the signal source. There's 1 kilohertz and 2 kilohertz as well. So if you want, you could simply low pass filter to say, I'm going to keep everything above that point, so I'm going to keep these high frequency sources, and I'm just going to completely eliminate these low frequency ones. And so I'm only going to detect higher frequency sources. So that's one way to do it. The other way is that you could do band pass filtering. So you could say, I'm going to detect each individual light source, and this is sort of what's needed for the open source project, and say, I'm going to make a filter to detect just 500 hertz, just 1 kilohertz, and just 2 kilohertz. When we define the filters, there's a few sort of names you should be familiar with. So there's the idea of the pass band, which is what's the frequency. And when we use this omega p here, by the way, this means we're talking in radians per second. You can convert between radians per second and frequency easily. In hertz, you'll see both used. So we have what's called the pass band. So this is for a low pass filter, but you should get the idea of the notation. So the pass band is the frequencies between with what we're saying signals. If the signal is within this frequency, it passes through the filter without being attenuated. So the other axes here is, you can consider it gain or attenuation or something. So as it goes negative, it means it's attenuating those signals more in those certain frequency bands. Below some frequency, we have the stop band here. So everything here we're saying has been attenuated so much it's effectively gone for everything we care about. So that's what we call the stop band. In between accepting and rejecting the signal, we have this transition band. So these filters, none of them are perfect, so it doesn't go perfectly from allowing signals to stopping entirely. There's a slower transition, and how slow that is depends on the filter design, between which it's attenuating more, but we can't quite consider them entirely gone. And this obviously will depend on your system. Do I have that? No. So if you had a very, very strong signal, very close to the signal you want, it's more difficult to attenuate the unwanted signal. So, and this sort of leads into the real filters. So they don't have these perfect transitions between the pass band and the stop band. So what do we define as the cutoff frequency? And one second, something disappeared from my slides here. Okay. Well, basically, we define the cutoff frequency as a portion of the magnitude. Yeah, this won't make sense without the. Let me just grab this here. We define it as a ratio of the regular magnitude. Come on. Sorry about that. I don't know why that. Disappeared on me, and maybe it won't connect. So I'll come back to that once it's connected. But basically, we'll be doing this because what we're going to be using is what's known as the half power point. So the half power point is where the power is half of the output power. It becomes half of what the maximum output power was. So at that point, if we go back here, what we're calling the stop band will be wherever the power here reaches half of the output power. And it looks a little weird on this diagram because we're using what's known as something called decibels. A very brief note on the decibel scale, it's a form of the power ratio. So when we talk about filters, we'll be using this notation of ratio of powers. What's the output power when we put a 1 kilohertz signal in? What's the output power when we put a 10 kilohertz signal in? Stuff like that. Decibels are very simple. We have an output to input power ratio. So, it might say the output power is 0.1. The output to input power ratio, so if I have, 1 milliwatt out and I put 10 milliwatt in, it has this ratio of 0.1. So it attenuated this one frequency by a certain amount. And when we use decibels, we convert them by taking the logarithm. So we go logarithm of this ratio. Gives us what's known as a bell. Bell is simply just this logarithmic ratio. And we use decibels, which means we multiply by 10, the deci prefix. So 10 log ratio. This is solely for power. It's important to note, so you'll see decibels throughout sort of everything you'll do. And it's important to realize it's always talking about power ratios. If you're using voltages, this is the trick. If we want to talk about a voltage ratio, so say we have this filter we're designing, and I say I put 1 volt at 10 kilohertz in, and I get 100 millivolts. Well, it's still at 10 kilohertz out, because I'm trying to figure out what the frequency response of this filter is. And I say, I want to make sure what's the half power point or something like that. So I can sweep it through and do this measurement. The incorrect way to do this, if you just go, 100 millivolts over 1 volt, and and applying decibels like this gives me whatever my answer is. It's incorrect because decibels are only for power. So the easy way to solve this is we just square the voltages. The power is related to the square of the voltage in electronics. So if we square that voltage ratio, it gives us the power ratio. Because we can easily take that square out of the logarithm, and it just becomes 2 times 10 log. The other format you'll see of decibels is this 20 log format. So this is used for voltages or when it's not explicitly power, is often sort of the notation used. In this case, if you wanted to get what is the attenuation or gain in decibels, you would use this 20 log of 100 millivolts over 1 volt. That's totally correct now. So now you've characterized your filter correctly at that frequency. And you could actually simply sweep the frequency through to generate a graph showing, what's this filter look like when you're testing it. Normally, so if there's clearly a power aspect, just using decibels in general, they're used for all sorts of stuff, like RF power. We'll use this 10 log of the ratio. If there's no clear power aspect, the example being, voltage is the simplest one, voltage gain. People have sort of abused it, so there's stuff like damage ratios in assessments that they want to measure in decibels, and they'll use the 20 log. If there's no clear power in that, it's not clear that it's directly related to power, this damage ratio. So that's not something that's part of electronics, but because you see decibels everywhere, it's important to realize there's really 2 main definitions, and occasionally people don't do this correctly and you get vastly wrong errors. So you really have to consider, is this ratio a power ratio? If so, I need to use 10 log. Is it not? Is it a voltage ratio? I have to use 20 log, because if we square the voltage, we get the power. That's where that comes from. And when you're looking at data sheets, this is something that came up in one of the earlier assignments. A few people had questions. I just wanted to sort of make sure everyone knows about this. You'll often see these logarithmic scales, and we'll see them all the time in these frequency response graphs. And in the logarithmic scales, you can see sort of the uneven spacing of the axes. And all you have to remember is that every increment here is a doubling, so you can see it goes 10, 20. This line is 30 because, or not a doubling, sorry, an increment based on the this base here. So when we get to this section of the scale, each tick is an increment by 10. So you can see it goes 10, 20, 20 to 30, 30 to 40, 40 to 50, etc., up to 100. Once we reach this next decade here, we now increment by 100 each time. So it goes 100, 200, 300, 400, 500, etc. So you just have to be familiar with the logarithmic scale, being able to recognize it, because it's in almost all the data sheets. Simply use it like this. They don't say anywhere explicitly what this is, but you should just be very familiar with recognizing the decade progression and what the increments look like on the logarithmic scale. And you can see the same thing. So in this case, we have this was from an earlier graph I had up. The frequency is being plotted logarithmically. So again, we increment by 1, 200, 300, 400, etc., up to 1,000 hertz, and then it becomes 2,000 hertz, 3,000 hertz, 4,000 hertz, up to 10K, and then 10 kilohertz, 20 kilohertz, 30 kilohertz, etc. And of course, you also see double logarithmic scale, so each x and y is using that format. When we, rather than having that double logarithmic scale, we'll instead plot the frequency response in decibels. And again, decibels is simply a ratio. So in this case, they explicitly call out relative ratio in decibels. But generally, that means that 0 decibels is the input and output power are the same, or voltage if you're using voltage-based definition of it. But in either way, the 0 dBs is always means the input and output ratio is the exact same. As we go negative, the output ratio is, or the output is lower than the input. As we go positive, the output is higher than the input. And again, it doesn't show it in logarithmic, the scale, but because it's in decibel, it's a logarithmic interpretation. So minus 10 dB really means, if you go back to our little graph here, you know, a 0.1, a change in the power, it's 1/10 of the output power of the input. So it quickly falls off. And if you go up to, you know, like 20 or 30 dB, you're talking that negative 30 dB, 1/100th of the output power as the input. As I mentioned, it's only a ratio, so you always have to have a reference. For the frequency, all these graphs, the reference is just the input power. In other things you'll see, just as a note, you'll see stuff like dBm, which is explicitly calling out, we are referencing this value relative to 1 milliwatts. And so you'll see dBW relative to 1 watt of power. That's all the time in RF. It's simply a way of saying relative to a milliwatt, what is the value here? So, and the reason we use dBs, if we have to have, you know, a huge variation of power, it's a really convenient and easy way to represent it. And later we'll have some niceties when we're combining amplifier stages in how we analyze that by just adding decibels. All right, so the final thing to show you is actual filter design. This is the part that's really useful. Really basic. The easiest type of filter is a RC resistor capacitor low pass filter. So we can do low pass or high pass or band pass with these RC filters. So it just needs a resistor and capacitor, so very limited requirements. And this breakpoint again, which is the half power point, which is what we also call this minus 3 dB. So minus 3 dB is equivalent to half the output power as the input. So that's the reference we're using here, or half the output power as compared to, you know, the regular at 0 or whenever the full pass band is. And it's simply in radians 1 over divided by the value of the resistor and the capacitor. You'll obviously see, because most of the time we're in frequency, in hertz, sorry, what you'll see is you'll also see the 2 pi in there worked into the equation to convert it to hertz. We can also do a high pass filter, and again we have the same breakpoint. In fact, just the resistor and capacitors are switched around. And if you want to sort of intuitively analyze, if you can't remember which way is it supposed to be, all you have to remember is that at high frequencies, a capacitor is basically a short, and at low frequencies, like DC, the capacitor is basically open. So you know this is a high-pass filter because in this configuration here, at very high frequencies, this capacitor you could replace with a wire. And therefore, the output voltage will be just related to the input. At low frequencies, the capacitor is removed from the circuit effectively, and this output voltage will just be pulled down to ground. So if you sort of remember the very basics of capacitors and how they behave with frequency, you won't have an issue. We can just combine two a low pass and a high pass to give us a band pass filter. And that's sort of the easiest, simple way to do it, is something like that. If you want to design these, you can use online tools. So I have a link here. I like this website. The trick is that you often only have a certain capacitor value. So you have, this 100 nanofarad capacitor in your kit, and you say, well, I want to use 100 nanofarad. I have a 1 kilohertz cutoff I want. What's the resistor value? You can get, sort of any resistor value from Mark, so that's a lot easier to deal with. In this case, I said 1 kilohertz, it gives me 1600 ohms. You'll have to slightly round it to whatever the nearest real values are. There's only certain values you can get. So in this case, 1.6K is works out. You know, it said it wanted 1592 ohms. We can get 1600, which is close enough. And these values are only good within plus minus 5%. So it doesn't really matter. You know, that's well within the sort of error we'd expect. And then we can graph it. So this is using that same, the simulator I referenced earlier. It can do these nice frequency graphs. So you can see I've plotted between 1 hertz and 100 kilohertz. The solid line here is the amplitude response. And this is in dBs again. Remember when we were talking about dBs before. So you can see the minus 3 dB point is somewhere around here, which works out exactly almost to 1 kilohertz. And if you want to know, if you say like, well, I have a 10 kilohertz source at some amplitude, how much will it be attenuated? This is the issue. We have some, you know, some other power, and we want to make sure that that 10 kilohertz source, you can read off that, well, it's going to be diminished by minus 20 dB. We can go back to the charts, or you can solve for this to figure out what is the actual ratio of power that will be diminished, or what is the ratio of the voltage change. As a note, this is where we can start playing a bit with, well, what happens if the sensor has some resistance in here? So I've added a 1 kilo ohm sort of sensor impedance right before this RC filter. And what you see is the 3 dB point has shifted, if it's probably around here somewhere. So rather than being 1 kilohertz, it's somewhere around 700 hertz. So just the effect of that sensor series resistance has shifted the response of our circuit. So that's what I mentioned a while back talking about buffering. When we use these filters, you may run into issues there. The other problem is loading. So at the output of the filter, now I've added a 100 ohm resistor, because maybe this filter goes into either a second filter or is driving a transistor circuit or something, you know, something with a high load. And in this case, what's happened, two things have happened. One, the output, because of the voltage divider, you can see the pass band, in the pass band, the output is now like minus 30 dB. So we've attenuated the signal a huge amount, and that's simply due to the voltage divider ratio. The other thing we've done is the frequency, the cutoff frequency has pushed way up here to somewhere like 10.2 kilohertz or something like that. So we've drastically changed the low pass filter frequency response. So those are things you have to be aware of, and you should either simulate your circuit or test it. And again, you can test it using the signal generator in the lab with the oscilloscope to plot the response. The other thing you might need to do is move around the cutoff frequency. So in this example here, what I had is a very strong signal at 10 kilohertz. So this green signal is the input, which is 10 volts peak to peak, this 10 kilohertz signal. And then the 1 kilohertz signal is the signal I want. And it's just a 1 volt peak to peak signal. And you can sort of see on this waveform, the slower signal here, this is the 1 kilohertz one. The problem is that the output of the filter in light blue here, I think I have a better view of it, hasn't sufficiently, you can kind of see the blue hopefully, it hasn't sufficiently reduced that 10 kilohertz signal. It's still very prevalent in our output. We can see it's, you know, it's not remotely as bad. That now the 1 kilohertz signal is of a similar amplitude probably to the 10 kilohertz, maybe a little more, but there is still quite a bit of that 10 kilohertz noise. So what you might need to do is, going back to our filter design, what we can do is we can shift the cutoff frequency even lower. So what we might say is that we're going to shift it such that it starts to roll off, you know, like this instead. So we're going to roll it off at 500 hertz or whatever that frequency is there, or like 200 hertz. It looks like I picked randomly. So what this means is that yes, our 1 kilohertz signal will be attenuated, but also our 10 kilohertz signal may be attenuated even more. In this case, you may maintain that same ratio because you have sort of a linear looking logarithmic slope there. So that might not help you. You may need to go to instead using higher order filters, which is where we'll talk about using the op amps next. But it's something to consider because if you had originally, for example, said, well, I want to roll off at 2 kilohertz because I want to make sure that 1 kilohertz signal gets through okay, you wouldn't have done the most reduction of that 10 kilohertz signal as you could because you don't really roll off, your 1 kilohertz signal is here, and you're not starting to roll off to well after it. So you should always consider where that cutoff frequency is to maximize the difference between the two signals. And this is especially important because you may select, so in this example here, the original 1 kilohertz roll-off was almost perfect because we're trying to capture that 1 kilohertz signal, so it starts to roll off. But because of loading effects, it might shift the actual roll-off frequency around, or we don't have perfect components, so you may want to give yourself some leeway. All right, so the final thing is active filters. So active filters are using op amps. We talked sort of briefly about op amps. Op amps, they provide a lower output impedance. You can possibly add gain with your circuit. You can add gain with the same circuit, so if you want to do some amplification. And we can also design what are known as higher order filters. So if we want sharper roll-offs, then with the simple RC filter, this is a really easy way to do that. You can design higher order RC filters as well, but it may get trickier with how much attenuation you end up with in the passband. So there's a few online tools. I just recommend these tools instead. Previously they used Filter Pro, Texas Instruments. This one's even sort of more straightforward in my opinion. So let's see if this works. So when you go to the web page, it gives you some ad that comes up first. You can ignore that. And basically you just pick, hey, I want this type of filter. And we can choose, in the passband, how much gain do I want? And I want that negative 3 dB frequency of, say, 10 kilohertz or whatever. It then asks you in the stop band, so at what point and how much do I want it attenuated? Based on what you set that, it'll select your filter design. So the only thing, if we go through the example I have here, it gives you an example. It says, well, based on what you told me, here's a filter. The only thing to watch out for, and it'll also do this issue where you have to assign correct values to the resistor and replot, possible values to the resistor. The only issue is that, if I give it a really tricky design, it'll create this super complicated filter. So it tells you right when you're doing this stuff here, it's saying at the bottom how many stages are in the system. This 3-stage design. The more stages basically means you need more op amps. So depending on how we want to respond. So if we accept some variation in the passband, we see the passband isn't as perfectly flat as before, it may be able to generate a easier filter. The other thing we can do is relax. So if we say, well, I don't need minus 40 dB, minus 30 would be okay, it may be able to generate even simpler to build filters that use less of your op amps. So in this case, I can go down to 1 stage. So if I go to 1 stage, that's going to mean there's just 1 op amp with the resistors and capacitors around it. So it's much easier to build that than if you had 4 op amps and you have to use a whole chip for 1 filter. So that's the only thing to be concerned about. And really the way to do that is to figure out what is the frequency, how much do I need to attenuate? What's the minimum amount I need to attenuate this other signal I'm worried about or I want to eliminate, to know what the stop band attenuation can be, which then defines how many stages you have. You want to get away with as few as possible to give yourself the most op amps to use. All right, so that's sort of a summary of everything. So the last of all that filtering, I hope will be useful. We'll come back to that a bit. There should be some more time on that, but experimenting with them is really the best way. Both in the circuit simulators are really easy to wire one up and plot the response. It's also easy to test them in the lab. So you have signal generators, you can set a frequency in, you can watch what the output is. As you increase the frequency, you should be able to observe the voltage going down. Without testing that you're working, if you just build it and hope it works and then wonder why your interference hasn't gone away, it's much harder to troubleshoot. As part of filters, we talked a bit about buffers. So we can use buffers either independently just to buffer a signal to give us a stronger drive strength, or we can use what are called active filters, which integrate the op-amp into the filter circuit itself. And the final thing is to be careful of the input voltages when you're connecting your filters or op-amps to your AVR. The filters or the op-amps will hypothetically generate higher voltages if you're powering them from the higher voltage source than that 5-volt system, and that could cause damage to your device, so you should be very careful and use the protection diode with a series resistor to prevent that. All right, that is it. Questions on that or anything?